So, what if a computer wasn't just on or off? What if it could be both and everything in between, all at the same time? It sounds like science fiction, but that is the bizarre, frankly mind bending reality of quantum computing. Today, we're going to take a journey all the way from a single, strange little particle to these massive machines that could literally change our world. Let's get into it.
Here's how we're going to break this all down. We'll start with the absolute basics, the qubit. Then we'll get into its spooky side, see how a quantum computer actually computes anything, look at the wild hardware being built, tackle the single biggest challenge holding everything back, and then finally we'll zoom out and look at the revolution this could all cause.
Okay, so first things first. To really get your head around quantum computing, you kind of have to forget everything you know about the simple classical bit that powers, well, pretty much everything in our lives today. Your standard computer bit is basically a light switch. It's either off, that's a 0, or it's on, that's a 1. It's that simple. But a quantum bit, or what we call a qubit, is totally different. It can be a 0, it can be a 1, and it can be a rich, complex combination of both of those states at the exact same time. And this isn't just some vague, blurry state. It's like having a whole new dimension for storing information.
This wild property has a name, superposition. You know, the best way to think about it is like a spinning coin. While it's up in the air, flipping over and over, is it heads or tails? Well, it's neither, right? It's in a state of both possibilities at once. It's only when it finally clatters onto the table, or in the quantum world when we measure it, that it's forced to pick one, heads or tails. That's the core idea of superposition.
And here is where the magic really kicks in, scaling up. With our normal computers, sure, more bits gives you more power, but it's a straight linear line. With qubits, because of superposition, the growth is just explosive. N qubits can hold 2 to the power of n values, all at once. That exponential leap is so huge that a quantum computer with just a few hundred stable qubits could process more possibilities than there are atoms in the entire known universe. Just let that sink in for a second.
So, if superposition is the first major pillar of quantum power, this next one is what takes things from weird to just plain spooky. And it unlocks a whole other level of potential. In fact, this property was so bizarre, so counterintuitive, that it really deeply bothered Albert Einstein himself, one of the guys who helped create quantum mechanics. He famously called it spooky action at a distance. And, well, you're about to see why. This is entanglement. You can take 2 qubits and link them in such a deep way that their fates become one. If you measure one and find out it's a 0, you know instantly that its entangled partner is also a 0. And here's the crazy part. It doesn't matter if that partner is a millimeter away or on the other side of the galaxy. It's a connection that just seems to defy our everyday rules of space and time. Okay, so we've got superposition exploring a mind-boggling number of possibilities, and we have entanglement creating these powerful, spooky connections. But how do you actually turn all that quantum weirdness into a calculation that gives you the right answer?
Well, the secret ingredient is a third quantum trick, interference. The best way to picture it is like ripples in a pond. When 2 waves meet, right, they can either add up to make a bigger wave, or they can perfectly cancel each other out and leave flat water. A quantum algorithm is basically a brilliantly choreographed dance that's designed to make the waves representing the correct answer get bigger and bigger, while all the waves for the millions of wrong answers perfectly cancel each other out.
So here's the whole recipe in 4 steps. First, you put your qubits in superposition to explore that massive ocean of possibilities. Second, you entangle them to create these incredibly complex relationships between them. Third, you run a series of very precise operations. These are called quantum gates, and they create that interference pattern which dials up the probability of finding the right answer. And finally, you measure, and poof, the whole system collapses down to one single classical answer, which, if you designed your algorithm right, is the solution you were looking for all along. Now, that is the beautiful theory, but actually building a physical machine that can control these incredibly delicate states, well, that's one of the greatest engineering challenges humans have ever faced. And it turns out there isn't just one way to build a qubit. There's this huge global race going on, with scientists and engineers trying all sorts of things. Some are using tiny superconducting circuits that look a bit like modern computer chips. Others are trapping individual atoms with lasers, or even manipulating single particles of light. Everyone's trying to find that perfect balance of speed, stability, and of course, the ability to scale up to thousands or millions of qubits. Let's just look at the 2 big frontrunners right now. On one hand, you have superconducting circuits. They're built like computer chips, and they are blazing fast. The problem? Their quantum states are super fragile and can vanish in a fraction of a second. Then you have trapped ions. These are literally single atoms held in place, and they are the complete opposite. Their quantum states are incredibly stable, lasting for a really long time. But the downside is that operating them is way, way slower. So right there, you have this fundamental trade-off. Do you want pure speed, or do you want rock-solid stability? And that fragility, that brings us to the single biggest roadblock in all of quantum computing: errors. Qubits are, well, they're like divas. They demand absolute, perfect isolation from the outside world. The slightest vibration, the tiniest change in temperature, can completely wreck a calculation. This process of losing your quantumness has a name: decoherence. Any little unwanted bump from the outside world basically acts like an accidental measurement, and it forces that qubit to collapse out of its beautiful superposition, corrupting all the data. Honestly, decoherence is the #1 enemy of every quantum engineer on the planet. So how do you fight back against this constant threat of decay? The answer is something called quantum error correction, or QEC, and it relies on massive redundancy. The idea is absolutely brilliant. You take the information of one perfect, hypothetical logical qubit and you spread it out across many noisy, unstable physical qubits. Then you can cleverly monitor the whole group for any signs of an error and fix it, all without ever actually looking at the precious information itself and destroying the whole computation. But the amount of overhead you need for this is just, it's staggering. Right now, the estimates are that it could take up to 1,000 of today's physical qubits just to create and protect one single stable logical qubit. And that is why we're still a long way from having machines with thousands of useful logical qubits. So this is basically the road ahead. Right now, we are firmly in what's called the NISQ era. That stands for Noisy Intermediate Scale Quantum. Our machines are pretty cool and powerful enough to do interesting things, but they're just too error-prone for the really big problems. The next giant milestone is what's called QEC break-even. That's the point where our error-corrected qubit is finally more reliable than any of its individual parts. And from there, we can start building truly fault-tolerant machines that can actually solve some of those world-changing problems. So let's just imagine for a second that we do it. We overcome all these massive challenges. What's the payoff? Why does any of this matter? Well, let's take a look at the revolution this technology could kick off. The potential applications are really and truly transformative. Look, quantum computers aren't going to make checking your email any faster. They're designed to solve problems that are fundamentally impossible for even the biggest supercomputers we have today. We're talking about designing new medicines and new materials by perfectly simulating molecules, creating way more accurate models of financial markets, and optimizing enormous, complex systems like global supply chains. But, and this is a huge but, with all that incredible power comes a very profound risk. There's a quantum algorithm that was discovered way back in 1994. It's called Shor's algorithm, and it just so happens to be perfect for breaking the exact type of math problem that protects most of our digital world. A future large-scale quantum computer could threaten everything from our bank accounts to our national security secrets. Now, the good news is, we're not just sitting around waiting for this to happen. There's a massive global effort already underway to build a defense. It's called post-quantum cryptography, or PQC. These are basically brand new encryption methods built on different kinds of math problems that we believe are hard for both classical and quantum computers to solve. And this is the really important part. They're being designed to run on the very same computers and phones we all use today. So in the end, it's pretty wild when you think about it. We're building this completely revolutionary new technology on the back of particles that are, by their very nature, uncertain, spookily entangled, and incredibly fragile. It holds the promise to solve some of humanity's greatest challenges, but it also creates entirely new ones. So the real question isn't just if we can build it, it's are we ready for the world it's going to create?